Okay, so I'd love to introduce the next speaker. His name is John Pacific. He's a cryptographer at Cipher. Thank you.
Hello. Yep, my name is John Pacific. I'm a, oh, there's no slides over here. No worries. I'm a cryptography engineer at Cipher. What Cipher is, we build cryptographic infrastructure for privacy-preserving applications and protocols. Oop, I'm actually not ready for this yet, but I will edit in. Can we get the slides up first? I'll switch to the demo in a bit. Oh, there we go. Great. Yeah, so I'll start again. I'm John Pacific. I'm a cryptography engineer at Cipher. We work on the privacy-preserving protocols and infrastructure for decentralized applications and things like that. We have two main product offerings. One is our proxy re-encryption network, which is something like a distributed key management system for decentralized apps. Our other one is called FHE, which is a fully homomorphic encryption library. It is currently the fastest FHE library available. And I'll be going more into what FHE is here in this talk, as well as showing off a demo. Oh boy, is this how this is gonna go? Oh, there we go. So what is fully homomorphic? We'll be going over what is fully homomorphic encryption, solutions for an FHE-based approach to secure computation, our Vanguard demo, which is something I wrote a while ago, and just to be clear, there is a more detailed version of this talk. I've been given time constraints, so it will not cover a lot of the things in detail that originally had. So if you would actually like to see a very big, detailed talk on this, please go watch the one I gave at ZK Summit. So secure computation solutions like fully homomorphic encryption are very simple, relatively simple in concept. We have software-based security protocols like FHE, which are implemented in software and not necessarily in hardware, unlike things like TEAS or like trusted execution environments, which I don't think are that secure. And also, these things are also implemented usually with hard mathematical problems that make things more secure. So in the case of fully homomorphic encryption, the most practical solutions are implemented with lattice-based hard problems. That's lattice-based cryptography. With hard problems such as learning with errors, which are also quantum resistant, if you're interested in that. Solutions exist for both single and multiple parties. So we can perform a computation as a single party, or we can perform a computation with multiple parties. So we can have like 3 parties perform the same computation, or we can have 1 party perform the same computation. So there's different applications for each, but we'll be going over the single party use case here. The function is computed directly on the ciphertext. The output of the homomorphic computation is equivalent to the computation performed on the plain text. So for example, let's take mathematical addition, right? So if we take 2 numbers and we add them together, say 2 plus 2, we get 4. If we do that in the plain text, we can see the inputs to that addition function, 2 and 2, and as well as the output 4. However, with fully homomorphic encryption, if we encrypt the 2 inputs, 2 and 2, so now we have encrypted inputs, A and B, and we perform a function like addition on it, we can add A plus B and get an encrypted output C, where the party who performed the computation doesn't actually know what was computed. There's 2 keys involved in many protocols like this. There's usually the encryption key. That's what you would use to encrypt data and decrypt the data, as well as something called the computation key that enables the computation on that encrypted data. So you can delegate who has the ability to perform this computation. That's very important for your security as well. This is also otherwise known as the bootstrapping key. So we're going to get into a little bit on the intricacies of FHE now. So some things like circuit design. I'm going to be going over a little bit of the pros and the cons associated with FHE right now, because many people believe that FHE is actually impractical right now, but I will show in a bit that that's not the case anymore, and that there's actually other problems that exist for us that keep us from making this a really practical thing right now. But we're very, very close to getting this, and once we do, we will be able to implement many incredible things. So one of these problems is circuit design. There's several cool things with it, but branching, for example, if you're ever used to computing something like a conditional, if you do if A, then B, else something else, right? So we can't necessarily do that in FHE. It requires pre-computed values or interactivity between interested parties. Interactivity between the computing parties. As you can see in this diagram here, that selection code decision branch there, it's not really possible. We also have FHE compilers. They're being researched to easily construct Boolean circuits. So in FHE, you build circuits using Boolean logic, like XOR, NOR, and things like that. One of our hackathon winners at ETH Denver actually implemented a WASM interpreter for FHE in Rust. So it would compile from Rust to WASM, and he would interpret the WASM to perform to just pretty much execute FHE code. It was actually very, very incredible. So I have a link in the presentation in the slides. It's for that project itself. There's also another project by Chris Piker, which is a more academic project called Alchemy. It stands for a language and compiler for FHE made easy. I've also provided a paper to that. It's written in Haskell. It's pretty cool. There's also various schemes that exist for different use cases here. We have schemes like HEAN, TFHE, and an interoperability framework like Chimera. HEAN stands for homomorphic encryption of approximate arithmetic. So essentially what approximate arithmetic is, it's useful for something like machine learning, where you want to compute some value, but not perform the actual, like the exact value. You want to get very close. It's great for machine learning. TFHE is for binary operations, so that's where you do XOR, NOR, etc. Chimera just allows you to transform ciphertext in between these frameworks. I'd go into more detail, but I'm kind of running out of time. So FHE is inherently malleable, meaning anybody can perform the computation on it, which gives us a few security problems. The highest security that we can get for it is chosen plaintext attack for fully homomorphic encryption, but there exists another type of FHE called leveled fully homomorphic encryption, which limits the circuit depth and prevents some arbitrary computations. This enables us to actually build a chosen ciphertext attack security. And we also believe that we can use zero-knowledge proofs to prove correctness to prevent malleability. So this is something we're actively researching. Bootstrapping is the process of how you make it as a partially homomorphic encryption scheme or a somewhat homomorphic encryption scheme into a fully homomorphic encryption scheme. Leveled FHE doesn't require this assumption for bootstrapping, but bootstrapping is a very strong assumption right now. It's not that great. Oh, I have a typo in that actually. Ciphertexts are large due to this construction here. 1 megabyte is equivalent to 16 gigabytes in TFHE. And ciphertext compression does exist where we can use stream ciphers to compress it and then decompress it by performing a stream cipher decryption in memory. HEAN potentially only has 40 times the expansion, but that's we're still looking into that more. Performance speeds can be improved from GPUs, ASICs, and FPGAs. New FHE is a GPU-based library. We've improved, as you can see, over 100 times over the leading implementation. So I'm going to dive into Vanguard a little bit here. It's the socialist millionaires problem. So if you're familiar with this, it's actually pretty simple. Alice and Bob are both millionaires. Alice wants to know if Bob has the same amount of money as her. But Alice, and this is the key part, Alice doesn't want to reveal how much money she has to Bob, nor does Bob want to reveal how much money he has to Alice. In essence, we're essentially computing a function, that computes the equivalence between the two inputs privately and in zero knowledge, and outputs whether or not they are equivalent without actually revealing that to the computing party. So Vanguard, what Vanguard is. I originally came up with this at ETH Berlin in 2018. I wrote down the idea I had on a pizza box because I had nothing else in front of me. It was not good pizza, so I just threw it away afterwards. But the diagram displayed is actually really problematic, so don't think you can take pictures of it and take it home and try to use it. It's not worth anything. Vanguard is a proof of concept that I'll be showing off. So I'm going to go over what the demo actually does here in Vanguard. First, Alice will encrypt her value, and then this encrypts a secret value. So Alice has a secret value. She wants to know if Bob has the same secret value. She encrypts that value. She then sends a tuple to Bob of her encrypted secret value and her computation key so Bob can perform a computation on that value. Bob creates a homomorphic constant of his secret value as well. Be aware that this constant is just a learning with errors problem, and it's trivial, which means we can easily decrypt it. So it's not encrypted at all, and it should not be treated as an encrypted value. So yeah, just be aware of that. Bob performs a homomorphic comparison using binary XNOR logic and aggregates the result using AND logic gates to prevent leakage. What that means is, if we simply were to compute and a comparison, we'd obviously see the compared bits, and we could know and guess eventually at what it is. So we have to aggregate those values into either a 0 or a 1. So we have to make sure that the inputs are equivalent, are relatively same size, and then perform the computation, and then compress it or aggregate it until we either know it's just true or false. Bob then sends the encrypted output of that computation to Alice. So it's either like an encrypted 0 or a 1. And Alice will decrypt the output to reveal the result of the encrypted comparison. So I'm going to go ahead and jump on this thing here. So let me SSH into a GPU box I have on AWS. And I'm actually going to be showing off a little bit here of what we do in Vanguard. I'm going to go into a little bit of the server. Yeah. How's that? Was it good? Cool. All right, so what we do for the input is we actually do a hash of it just so we can get the input to this, with this computation of like a similar size. We just need it to be the same size as any input. We hash it, and then we compare secrets here, right? So this is where, right here, where Bob creates that value, that toxic value where he said it's unencrypted. That's his unencrypted secret that he's going to compare to an encrypted secret. So this encrypted secret is actually Alice, who's going to send it over to Bob and perform this computation. This encrypted comparison is the output of this encrypted operation. And then we just return that. So let me open up over here. What Alice is going to send so here Alice encrypts a secret, her own secret that she doesn't want to reveal to Bob. She performs a hash of it just so we can, like I said, we need those inputs to be uniform. And then she encrypts it and then sends that computation key and the encrypted secret to Bob. So what Bob is going to be doing is computing on this encrypted data. To be clear, Bob does not know what the plaintext value is. He's going to compare his secret to Alice's secret and not have any knowledge of whether or not it's the same. So let me just do some Python mumbo jumbo here. All right, so what I'm going to do is I'm going to run this server code here. And so it takes as an argument Bob's secret. It takes as an argument Bob's secret, and we're going to go ahead and put that as my very secret, okay? So Bob is now running just running his server, wanting to see if anybody can see a secret and providing a public service, right? So Alice is going to try to say, okay, I want to know if Bob has the same secret as me, but I don't want to reveal to Bob that I have that secret. So let's say we put in the wrong secret first. So my very secret, wrong secret. And it takes a while to perform the first homomorphic comparison because it actually has to compile the circuit and run it. But after that, we can actually run it really quickly. So it finished. Bob does not have the same value as you, but doesn't know that he doesn't. That's weird worded, but essentially Bob doesn't know that Alice has the same value, but he did the comparison. All right, so this has applications to market matching, to dark markets where maybe you want to know if somebody's selling something, but you don't want to reveal to them what they're selling, what you want to buy, right? So I'll kill this right here, and I'll try it now with the correct value. My very secret. So watch, it'll be much faster now. Bob has the same value as you, but doesn't know that he does. See, and that's it. That's Vanguard. It's very simple. It's a very simple proof of concept, but it demonstrates fully homomorphic circuits. And something that you can do with FHE as well. I have one last slide. All right. So on a closing note, I just want to say that recently there's been a lot of debate in Australia on privacy. Let's be clear here that the politicians involved actually know very little of privacy and what cryptography is. Malcolm Turnbull, the 29th Prime Minister of Australia, said, "The laws of mathematics are very commendable, but the only laws that apply in Australia is the law of Australia," which is a little insane. So yeah, let's be clear. This is a very big problem. We, as a space, need to realize that decentralizing privacy is the only way towards true freedom and privacy. Governed privacy will never work. We need direct action and privacy to actually have true freedom. So, thank you. We're new Cipher. Check us out.
John, so that was definitely very interesting. I guess for us who are not cryptographers, and given that I feel like I can actually ask you this question, can you tell us what the work that you're doing, how does that actually, preserve privacy and the political freedom of the commons?
Sure. So cryptography by itself is not necessarily a political tool, but it can be used as one. And privacy is much more simple than everyone really thinks it is. It's about consent. Privacy is literally just a digital form of consent. Society right now, I think, the reason why we see so many problems with privacy now is because society at large already has problems with consent. And I think that it's a function of that. And what we can do with cryptography is actually build applications, protocols, and infrastructure that require consent, that makes people think more about this consent and introduce it in their own lives. When we do that, we're going to see large changes, I think, in about how we think about politics and freedom if we can just simply think better about consent and maybe even economics.
And I just wanted to add to that, given that I was a former lawyer, is that most of the privacy laws actually govern the collection of information of governments and organizations, and it's definitely not there to protect the privacy of individuals. So what you've raised is actually quite interesting. We can think about consent issues and et cetera.
Absolutely. Cryptography, when asymmetrically used, it's a very violent act of aggression. When the governments and rulers and dictatorships can have privacy, but the commons can't, that's a clear asymmetric form of power, and it needs to be abolished.
Thank you so much.
Thanks.
Okay.